Hello everybody. We continue the section from the last lecture because in the title of that section there was a word products, but I didn't touch products in fact. So but let us call it differently. Multiplication of series. And we'll start with the following theorem. Theorem 1. If two series AN and BN converge absolutely, then the series NM from 1 up to infinity. No, it's not good. Sum A and BM, where the summation is over all possible pairs of indices and M and N in arbitrary order converges absolutely to the product of sums. To the product, or maybe it's better to the product. This product, not of, to the product. So, let me explain what we are talking about. How we multiply finite sums? We take products, so each term of the first sum is multiplied by each term of the second sum. So that is A1 B1 plus A so on A1 BM. Sometimes we do like that, plus AN B1 AN BN. So we consider all possible products, all possible pairs of indices from 1 up to n and from 1 up to m, and that is how we proceed with multiplication of finite sums. Now the question what to do with infinite sums. And we know that if series converge absolutely, then we have no problem with order. We can rearrange without any problem. And in fact, it turns out that also we can multiply like we did for infinite. So it means we can extend same rule to the product of infinite sums. So it doesn't matter in which order we choose this considering of all possible pairs. The theorem says the result will be the same. So, proof. Let us start with absolute convergence. So we consider partial sum. I'll write from 1 up to capital N. And how we can estimate it? We can estimate it by what? There is sum from 1, okay, I'll write n equals to 1 up to maximum of n modulo an times sum m from 1 up to maximum of m modulo bm. What I mean by max n and max m? The question about conditional convergence I will answer a little bit later. For a while, only epsilon. So, you see, what is maximum n? Max n, what I mean by max n, is maximal of all indices of an which can be found in the sum, partial sum of our series of A and B. So, look, here somehow we order pairs of indices, n and m. Of course, one index may happen several times. Same is true concerning m index. And you see, the order is absolutely arbitrary. And what we do, we look at this partial sum. It contains finitely many terms, and we look at the maximal of all indices of A n. So maximal of all such indices appears here. And you see that indeed this inequality is obvious because all those terms are non-negative, and here we multiply what is in the right hand side. It contains all possible products of all indices which may appear in the left hand side. So in the left hand side some pairs appear, and all possible indices which appear in the left hand side are taken into account into the right hand side. So, and we know, because of absolute convergence of both series AN and BN, that those sums are bounded. Hence, partial sums of our series are bounded as well. And it follows that the series AN-BN converges absolutely. Absolutely. Okay, first part is proved concerning absolute convergence. Now we start the second part about convergence of this series to the product. So for that reason, we'll use the result of former section, namely what we know. We know that if a series converges absolutely, then the sum will be the same for arbitrary rearrangement. So we can choose arbitrary order. Now let us choose a special rearrangement of pairs AN times BN. So by theorem about independence of absolutely convergent series, it doesn't matter which rearrangement to choose. For absolutely convergent series, it doesn't matter. So, what I want to do, I want to consider the following. So we start with A1, B1, then we choose A1, B2 plus A2, B1. Next, we choose A1, B3 plus A2, B2 plus A3, B1, and so on. You see, for each expression in brackets, the sum of indices of A, B is constant. So, first term, the sum is 2. Second, the sum is 3. Third, the sum is equal to 4, and so on. So, that is, in fact, it has a special name. I'll give it a little bit later. So, let us find a subsequence. Not find, consider a subsequence of the sequence of partial sums. And in fact, this subsequence will consist just of summation of brackets. So you see the first one, second one, third one, and so on. We know the series converges absolutely. So the sum doesn't depend on rearrangement. Doesn't matter how we rearrange our pairs. I choose this specific rearrangement. So we know there is a limit of partial sums. And I want to know what is the value of this limit. And if I know that a sequence has a limit, then arbitrary subsequence has the same limit, right? So if I have a sequence with a limit, then subsequence has the same limit. So subsequence of our sequence has the same limit as the whole series. So what is it? Let me write it down. That is sum k from 1, not from 1, from 2 okay, let's start from 1 up to capital N, Ck, where Ck equals to A1 B k minus 1 plus A2 B k minus 2 plus so on plus A k minus 1 B1. So you see the sum of indices for each Ck is equal to k always. In fact, yeah. No, I'll start with 2 because C1 is absent. C1 is absent. K starts from 2. The very first, for k equals to 2, we have A1, B1, and that's all. Okay. Now, look at this. So, compare it with the following. Compare it with A1 plus so on plus A capital N minus 1 times B1 plus so on plus B N minus 1. What happens then? Look, if we try to compute this product, we'll obtain similar thing. A1 B1 plus A1 B2 plus A2 B1 plus so on. But, of course, it will be different from what is written here. Why? Because, look, for example, we have a n minus 1 B1 plus, so the very last Bn minus 1 is considered, but after that I have extra terms like n minus 1 B2 and so on, which are not included into this sum, right? So you see, all terms here also exist over there, right? But what we can observe is that this, so note that A1 plus so on plus AN minus 1, B1 plus so on plus BN minus 1 is also a partial sum of a rearrangement. So of A and BM. So you see, this special rearrangement, I'll use it later in fact, but it is not very suitable for our purpose. And C1 here doesn't appear, B0 is absent, that is why. C1 is not considered. So, look, this special rearrangement I'll use in fact later. It was very early at that moment. What is essentially better is to consider that one. So, we consider that sum, right, this product, and that is a partial sum of a rearrangement. So, we know that arbitrary rearrangement has the same limit. And we know that a partial sum for such a rearrangement has this form. Right? So, what we can conclude? Hence, the sum of the series coincides with the limit as n tends to infinity, a1 plus so on plus an minus 1 times b1 plus so on plus bn minus 1. And that is precisely the product of the sum of our series. So let me explain once again the main idea, what we do. So, first of all, we prove absolute convergence of a series which contains all possible pairs of an times bm. So we take all possible pairs n and m, and we consider a series which is formed by those all possible products. And after that, we prove that this series converges absolutely. Hence, arbitrary rearrangement of this series converge to the same number. And the question is about what is this number is equal to. And for this reason, we consider such a product And you see, it consists of some pairs, right? Some pairs, of course, finitely many pairs of indices are included here. And I can choose a rearrangement of our series in such a way that among partial sums of this series will meet with all those products. So somehow rearrange in such a way that all those products will appear as partial sums with some numbers, doesn't matter, right? So we rearrange somehow, but in such a way that that product appear as a partial sum. After that, what happens? We know that arbitrary rearrangement has a limit. So arbitrary subsequence of partial sum has the same limit. And this is a subsequence of partial sum. And that subsequence has the same limit. And in fact, this limit is precisely product of the sum of our sets. Hence, we have proved that indeed, for absolutely convergent series, we can proceed as we did for finite sums. But for general case, it's essentially more complicated. So, let's consider general case, what we can do with product of series in general. And in fact, it was given before, so I will repeat it as a definition. Cauchy product of series sum n from 1 up to infinity an and sum n from 1 to infinity bn is the series sum n from 2 up to infinity cn, where cn equals to, so it was written before, k from 1 up to n minus 1, a k, b, n minus k. So the sum of indices is always equals to n. Okay. So that is the definition of Cauchy product. And now theorem 2, Merton's theorem. If, okay, for the sake of simplicity, I'll choose from the beginning one series to be convergent absolutely. So if the series A converges absolutely, the series Bn converges, then the Cauchy product converges and the sum equals to the product of the sum of those series. So proof. Of course, we cannot expect more general assertions because of, as we know, if a series converges conditionally, then rearrangements are very important. So we have to choose some special rearrangement if we want to have such a nice property, namely the sum of a product equals to product of sums. Okay, so I will choose some notations. Proof. So capital A n equals to, by definition, n from 1 up to capital A and n. Capital B n, partial sum of Bn. Capital Cn is partial sum of our Cauchy product. Also, so we know the limit of capital A capital N exists, so let it be capital A, the sum of our series of An. Limit of Bn equals to B. And also I'll use the notation for remainder, B minus Bn, or in other words, capital N plus 1 up to infinity Bn. These are all notations which I want to use. So, I want to consider Cn, partial sum of the Cauchy product. So what is it? A1, B1, that is C1, C2, sorry, plus A1, B2 plus A2, B1 plus so on, plus for the very last it will be A1, B capital N minus 1 plus A n minus 1, B 1. Okay. So, what is it? If I'll put A1 as a common multiplier, then what we have in brackets? B1 plus B2, so on, up to B capital N minus 1. Also, similarly, A2, B1 plus so on, plus B n minus 2, and so on, A n minus 1, only B1. We have only B1. That is A1 capital B n minus 1 plus A2 capital B n minus 2 plus so on plus a n minus 1 capital B1. Now, using notation for remainder, that is a1 bn minus 1 is capital B minus beta n minus 1 plus a2 capital B minus beta n minus 2 plus so on plus a n minus 1 capital B minus beta 1. And if I'll take common multiplier capital B, then what remains is a partial sum a capital N minus 1 times capital B minus gamma n, where gamma n by definition is equal to, so what we subtract here, a1 beta capital N minus 1, a2 beta capital N minus 2 plus so on plus a capital N minus 1 beta 1. That is the representation of our partial sum. Right? Beta. Beta, by definition, is here. Beta is here. Is defined like the difference. So that is remainder of our convergent series, or tail of this series. Okay. So now, what I want to prove? I want to prove claim. What is our claim? I want to prove that the limit of capital Cn equals to AB, right? The product of sums of our series. Now, what we have? Capital A n minus 1, as capital N goes to infinity, tends to infinity, right? Capital A n tends to capital A, right? So it means that this claim in our terms is equivalent to the proof that the limit of gamma n equals to 0. That is what we have to prove. Limit of gamma n, that is gamma n, is equal to 0. Okay, let's have a break. So we continue. Let me write in more details our gamma n. That is a1 beta n minus 1, a2 beta n minus 2. Now let me emphasize what I plan to do. So a m beta n minus m plus a m plus 1 beta n minus m minus 1 plus so on, plus the very last is a n minus 1 beta 1. So look, I split our gamma capital N in a place. And so I want to prove that gamma n tends to 0 as capital N tends to infinity, right? And now look, what we know about those betas. Betas are defined as remainders of convergent series, right? Hence, so what we know about beta n. Beta n are remainders of a convergent series, hence the limit of beta n equals to 0. That is one thing. But look at this expression. So, look, I split our sum at a moment m, right? And for a while, no restrictions to m. I want to understand how I can put restrictions. So, look, what we have here. Okay, we know beta n tends to 0, but here we meet beta 1, which is a constant, right? Definitely it doesn't tend to 0. It cannot be small, right? So, we can make this expression, I mean, the second half of our expression, we can make it small. How? Because of a should be very small, right? In which sense? In which sense they have to be small? Now I want to estimate somehow this expression, right? I want to estimate this expression. Betas, I cannot guarantee that they are small. But I can estimate it. Why? If I know that a sequence has a limit, then it is bounded. So, beta n is bounded. So, let's say beta n in modulus less or equal to m for all natural. Okay. Now capital M is given. So, I want to estimate the second half like that. Less or equal, modulo a n plus 1 plus so on plus modulo a n minus 1 times capital M. So, I estimate each of betas by capital M, right? Now, look. What is it? Sum of modulus. And we start from n. And we have a freedom in the choice of m. Now, the series converges absolutely. This series of an converges absolutely. So I want to use this fact now. Hence, remainders. So, firstly, n from 1 up to infinity modulo an converges. Hence, remainders so what remain if we start from m plus 1? they tend to 0 as m tends to infinity. That is by definition of convergence of a series, right? Hence, for arbitrary epsilon greater than 0, there exists m. I can choose such an m, right? And I'll choose it such that this remainder is as small as we want, and I want it to be less than epsilon over 2 capital M. Remember, capital M is chosen just suitable for all members of the sequence of remainders beta n. Right? Then look here. We start from m plus 1. Stop somewhere, doesn't matter where we stop, right? Because we know that the remainder, even if we don't stop at all, the rest is less than epsilon over 2n, right? So we deduce from this that is less than epsilon over 2 for this choice of m. So now look, m is chosen, right? M is chosen. Okay, m is chosen. Now look, the second half of our expression is estimated very well, less than epsilon over 2. Now what is for the first half? Look at numbers in betas. Capital N minus 1, N minus 2, so on, up to capital N minus 7. Remember, M is fixed, right? We choose it. M is fixed. But still we have a freedom in the choice of capital N. So, I want to choose capital N. How? Okay. How to choose? Okay. Let me choose. So the series of modulus converges, so let it be equal to, let's say, A star. A star is the sum of modulus of an. That is A star. Now, limit of beta n equals to 0, hence for arbitrary epsilon I can choose, there exists, let's say, n naught, such that for all capital N greater this, in fact, n naught for all, okay, I will choose just here n minus m greater than this n naught. It's equivalent to say that capital N greater than m plus n naught, but I prefer to write it like that for all n. So all capital N such that n minus m is that one. We have modulo beta n minus maybe that is not good. How to write it? Beta n for all n. Okay, let it be n greater than n naught, right? I'll write like that. Beta n less than, firstly, I'll choose for small n tends to infinity, right? Beta n less than epsilon over 2a star. And then, so what I'll choose, I want to have now choose capital N such that capital N greater than m plus n naught. That's it. So look, what happens for arbitrary n, capital N, like that? So I choose n naught from this limit, right? And if capital N greater than n plus m plus n naught, then what happens? I can estimate like that. Beta capital N minus 1 plus a2 beta n minus 2 plus so on plus am beta n minus m modulus less or equal. So replace. Look, what about numbers here? Indices of betas. Every index, so capital N greater than m plus n naught. So here we have index which is greater than n naught, right? Capital N minus m greater than n naught. Hence modulo beta less than epsilon over 2 a star. And it's true, of course, for larger indices as well, because for all. So I replace every beta by this number, and what remains? Modulo a1 plus modulo a2 modulo am. But this sum is less or equal than a star, hence, okay, maybe a star plus 1, let's say, to avoid difficulty with a star might be 0. To avoid it, I'll put here plus 1. So that is less or equal than a star, so altogether less than epsilon over 2. So you see, look, now for arbitrary epsilon greater than 0, there exists n naught such that, in fact, there exists even n naught plus m. This exists, right? This index exists such that for all capital N greater than this index, we have estimate modulo gamma n is less or equal, strictly less in fact, epsilon over 2 plus epsilon over 2. That is epsilon. That's it. So the claim is proved and the theorem is proved. So you see a rather thin consideration, and of course it heavily uses absolute convergence of an, of the series of an. And this is in fact an essential restriction. So let me consider an example. Which shows that the product may diverge, even Cauchy product of two convergent series may be divergent. So, example, an equals to bn equals to minus 1 n plus 1 over n. So we know that the series converges, square root of n, square root of n, converges by Leibniz test. Now let's consider Cauchy product. That is sum n from 1 up to infinity Cn from ternary. So Cn equals to k from 1 up to n minus 1, ak b n minus k. In general, and what is in our case, sum k from 1 up to n minus 1 minus 1 power k plus 1 over square root of k times minus 1 power n minus k plus 1 over square root of n minus k. That's it. What is it? That is minus 1 to the power n plus 2, but minus 1 squared is 1. Sum k from 1 up to n minus 1, 1 over square root of k times n minus k. Okay. And I claim that so modulo Cn doesn't tend to 0 as n tend to infinity. So by necessary, that is what I want to prove, necessary condition for convergence, or shortly term test it is called also, right? Term test, necessary condition of convergence or term test. It implies that the Cauchy product diverges. So why Cn doesn't tend to 0, So, okay. I want to estimate Cn from below. Model of Cn. And for that reason, I need to estimate k times n minus k from above. So what is it? Look, what we have. If I'll draw a picture, I forget about k natural, so let's think k to be real. Then what happens? k0, kn, and the graph of this function k times n minus k is what? Is a quadratic parabola like that. So maximal value is in the middle for a quadratic parabola which intersects real axis at 2 points. Maximum is at the middle, and that is n over 2, right? So this value is less or equal than n over 2 times n minus n over 2, and that is precisely what? N squared over 4, right? N squared over 4. That is maximum of denominator, right? So modulo Cn is equal to the sum of those expressions. So every term under square root less or equal than n squared over 4, so we have greater or equal than sum k from 1 up to n minus 1, 2 over n. That is 2 times n minus 1 over n, and you see it doesn't tend to 0, right? Hence, Cn doesn't tend to 0 as well. So, you see, the Cauchy product of two conditionally convergent series need not to be convergent. Need not to be convergent. So, once again, look. If we have two series and we want to multiply them, then what may happen? If both series converge absolutely, you can do it without any restriction, right? So you can consider a series which consists of all possible products an times bm in arbitrary order. Doesn't matter, right? So this series converges and its sum equals to the product of sums of those two series, right? That's one case. Second case, precisely one of those series converges absolutely. Another conditionally, right? Then, of course, you cannot guarantee arbitrary order, right? Because even convergence of this series depends on the order. But you can consider Cauchy product, right? So, Cauchy product, Cn, k from 1 up to n minus 1, ak bn minus k, right? Cauchy product. Then Cauchy product converges, and the sum equals to the product of those sums. But if both series converge conditionally, then even Cauchy product may be divergent. But one more interesting story is that if Cauchy product converges, then for sure it converges to the product of those sums. So the worst thing which may happen is that Cauchy product diverges. But if it converges, then for sure the sum equals to the product of the sums of those sets. Okay, so too much of time I spent for this section. So 20.1 uniform convergence. Uniform convergence of sequences. So we consider functional sequence. So we have a sequence of functions. Each of them, all of them are defined on a set E. Okay, let it be in R. Then if we fix X, then we have usual sequence of numbers, of real numbers. And if we are talking about convergence of this sequence of numbers, then we call it pointwise convergence. So pointwise convergence. What is it? Pointwise convergence. For arbitrary x in E, there exists limit. That is pointwise convergence. Okay, let it be f and it depends of x belongs to R. So we have pointwise convergence. In quantums, let me explain. Or for arbitrary epsilon greater than 0, for arbitrary x in E, there exists capital N natural, such that for all n greater than this capital N, we have an equality less than epsilon. That is pointwise convergence. Look, capital N depends on epsilon and x. That is very important. It depends on x. And what is uniform convergence? Uniform convergence. Definition. Fn uniformly converges to F on E, and we use also such a notation for uniform convergence, two arrows simultaneously. If for arbitrary epsilon greater than 0, there exists a number, one number for each x, such that for all n greater than capital N, and for all x in E, we have Fn of x minus f of x less than epsilon. So what is difference? The difference is in the place of this quantifier. So you see, we interchange places of two quantifiers. for arbitrary x, and there exists capital N. So here, capital N depends on epsilon only. That's important. That's important. So, what is geometrically? Let me consider an example where we have no uniform convergence. Example. X to the power n on 0, 1. These are fn of x, right? Fn of x. So we know what is the limit. What is it? That is 0 for x from 0 up to 1 exclude 1, and 1 for x equals to 1. So we have pointwise convergence of our sequence to f of x. Let me draw a picture. So, look, what happens? Here I'll draw, let's say, x squared, right? Then x cubed, and so on. So what happens? Look, what means this inequality? It means that I have a neighborhood, epsilon neighborhood of f of x for arbitrary x. What it means? Look, I take here minus epsilon, epsilon, right? For arbitrary x from 0 to 1 exclude 1. So it means I should consider that strip, right, around every point except 1, right? But around 1 what? I should consider 1 minus epsilon, 1 plus epsilon. That's it. That's it. So, look. F of x plus minus epsilon is drawn here. F of x minus epsilon, that is f of x minus epsilon. Look, that is graph f of x minus epsilon, all right? Here we have horizontal interval with y equals to minus epsilon from 0 to 1, excluding 1, and that point. So, we have uniform convergence if all graphs of fn of x lie in that strip for sufficiently large n. And you see, that is not true, right? Look, doesn't matter how large n you choose, right? Look, what happens with graphs? Somewhere very close to 1, of course, right? But for sure, the graph of x to the power n intersects this line, right? And part of the graph will be outside of that strip, right? So, we have no uniform convergence for that sequence. So, not uniformly. Fn doesn't converge uniformly on 0, 1. And Okay, I have a couple of minutes to formulate an assertion, a proposition, let it be proposition, Fn uniformly converges to f on E as n tends to infinity if and only if the sequence of supremums modulo Fn of x minus f of x tends to 0 as n tends to infinity. Look, why it's true? Because that one, last one, for arbitrary x modulo Fn of x minus f of x less than epsilon, it's equivalent to say, so it follows and it applies in both directions, that supremum for x in E, Fn of x minus f of x. Okay, we cannot less or equal than epsilon. No, just implies, right? So if that is true, then supremum is less or equal than epsilon, right? But if supremum is strictly less, then for sure this inequality also holds, right? But once again, look, for example, that one. All others for arbitrary epsilon that exist, capital N and so on, they say that we have supremum tends to 0. Conversely, analogous assertion, analogous thing, completely analogous. Okay, I think I will not continue this section. No, no sense to continue, just so definition. Let me definition. So today we were able only to discuss the definition. I think it's a good point to stop. Okay, that's all for today. Thank you.